Okay, thank you very much, and thanks to the organizers for the invitation to give this talk here. So yeah, I'm going to talk about this time domain SelfForce code using discontinuous Galerkin called SelfForce1D that I've been writing in collaboration with Barry Waddell and Nils Burton from University College Dublin. This is, as Barry also mentioned, this code is part of the black hole perturbation toolkit, but it's also part of the ISN toolkit. So it's kind of, we thought that this code might be sort of a bridge between the two, the numerical relativity and the SelfForce communities. And so hopefully we will have some people start using it. And so just a little bit background about what Barry was also talking about, extreme mass ratio inspirals. So I will also, I should also say that I only have a few slides describing the code and so on, and otherwise we will switch to, I have a Jupyter notebook on the tutorial server that we can try to run, where we check out and compile the code and run some examples. So, but first a little bit about extreme mass ratio inspirals. And so we all know that supermassive black holes at the center of our of most galaxies are clearly surrounded by a cluster of stars, and some of these will be black holes or neutron stars or compact objects in general. And some of those can be brought into highly eccentric orbits by two-body interactions inside the cluster of stars. And if they get close enough to the central black hole, then we start having energy and angular momentum losses through gravitational wave emission that will shrink the orbit until the small object plunges into the supermassive black hole. So these can start out being really highly eccentric. Of course, the eccentricity will decrease over time, but will most likely still be significant even just before the plunge. And as Barry also mentioned, such systems are expected to be very important events for the space-based gravitational wave detector LISA that hopefully will be flying sometime in 2030s. And also, as Barry mentioned, it is possible to use perturbation theory and essentially treat the small object or the small black hole or neutron star as a point particle. And you can do that by decomposing the field produced by this small object into a singular and a regular part. So, as Barry also mentioned, the particle perturbs the space-time, and the perturbation propagates on the curved space-time and gets backscattered off the curvature or goes around the black hole, and eventually comes back and interacts with the particle itself to cause the inspiral of the orbit. The SelfForce1D code currently in the repository only supports, does not actually do gravitational perturbations. There are some project on the way to add that. But the first thing you can do is look at the simpler scalar charge case to use that as a sandbox for developing of new numeric techniques that we use here. So that is what I'm going to talk about now. Well, first, here's sort of a little artist impression of an EMRI. Well, this is not a very extreme mass ratio. This is actually, I mean, from looking at the size here, compared to that size there, it looks like something that might actually be possible to do with numerical relativity. But of course, in the limit of this object shrinking down compared to this, this is what we want to look at. So SelfForce1D is an open source code for performing time domain self-force computations. In the what Barry talked about in the black hole perturbation toolkit, most of the things done in Mathematica are done in the frequency domain, but there are some things that we probably want to do in the time domain, so it's also important to have those kinds of codes in there. So currently, the code involves the scalar wave equation, but as I mentioned, metric perturbation equations are being added as well. And currently, it only supports Schwarzschilds, but again, support for curves being added. That adds more complications, of course. So in the code, the scalar fields produced by the particle is are decomposed into Schwabe harmonics. And the end result of that is you get 1 + 1 dimensional PDEs in time and radial coordinate to be solved using the method of lines, and you get one equation for each specific Schwabe harmonic mode you have. So in the code, we use nodal discontinuous Galerkin method to discretize the PDEs in the radial direction. And this is when we use discontinuous Galerkin methods, that's built-in support for handling non-smooth features as long as those features are placed on the boundaries between two neighboring elements that we split our domain into. So the idea is that we know that the fields are not smooth at the location of the particles. You have because we're using the point particle approximation. But if we keep the particle located at the same at a boundary between discontinuous Galerkin elements, then we can still get exponential convergence with the order of the method away from that location. So in this code, we don't actually use a delta function source as a point particle, but we use something called the effective source that can be shown to produce the correct self-force as well. And so we do this. We have this kind of world tube approach where near the particle or around the particle we have a world tube, where inside the world tube we are only looking at the regular fields. So again, I mentioned in the beginning that when you do perturbation theory, you can decompose a point particle field into a singular field and a regular field, and it's only a regular field that is responsible for providing the self-force acting on the particle. So inside the world tube, we only see the regular fields, whereas outside we have the full retarded singular fields. And again, that of course means that we have discontinuities in our solution because we have these boundaries. But as long as we keep those the world tube boundaries located on element boundaries, we can still we can take care of those discontinuities when we communicate the fluxes from element to element and maintain exponential convergence. In order to do all of this with everything kept at a specific element boundaries, we have to use different coordinate systems in different parts of the domain. So near the particle, we either, depending on the orbits, if it's a circular orbit, we can just use torus coordinates. If we have a generic orbit where the particle is moving in the radial direction, we need to have some time-dependent coordinates that keeps the particle fixed at the same coordinate location. And then inside near the horizon, we use hyperboloidal coordinates to place the horizon at a finite coordinate location. And on the outside, we also use hyperboloidal coordinates to place square plus or future null infinity at a finite coordinate location. Of course, we also have to evolve the orbits, and we have two different ways of doing that, either using direct geodesic integration with forces, or through something called the oscillating orbits framework, where instead of evolving the coordinates themselves, you evolve the orbital elements like the eccentricity and simulated spectrum. And the advantage of those is that they evolve much more slowly than the coordinates themselves. We have implemented both some Roca-Cotta and some Adams-Basford multi-value methods for the time integration. We have implemented routines that we can extract the self force from the regular field at the particle location. And we have some other observers that can extract the fields at the horizon, and that's quite plus. It turns out that when you start a simulation, if you don't actually have the right initial data, you have to sort of turn on your source in a smooth way, and you get some outgoing waves that needs to propagate out of the system before you can actually get to the point where you get the right self force. But for low L modes, this can take a long time because they decay rather slowly. So we also have the option of using initial data calculated in the frequency domain for eccentric geodesics, especially for the low L modes, in order to avoid having to evolve a long time before these initial transients leave the computational domain. Back reaction can be turned on, but we still have some unsolved issues with instabilities that we are looking into. The code itself is written mostly in object-oriented Fortran, with the effector source provided in C++ routines, variable those, and the initial data from the frequency domain code is written in Python and was provided by Nils. So, sorry, what's that question? Okay. So the code requirements is that because it uses object-oriented Fortran, it needs a fairly modern Fortran compiler, but it has been successfully compiled with Fortran 70.3 and i.17 and newer. Just a caution: Ubuntu's installation of Fortran somehow is messed up, and every time I try to use it, I get an internal compiler error. I was able to compile Fortran from source on an Ubuntu system, and that works fine, so I don't know what they're doing. It also needs a C++ compiler, either G++ or the Intel ICPC should work. It needs Python, as it uses a tool called scont for building instead of make or CMake. And also the initial data files, if you want to use those, are produced by Python code. With regard to libraries, it needs BLAS and LAPACK, but only a very small subset of those routines, essentially for some very small matrix eigenvalues and calculations and small matrix inversions. So nothing that really requires high performance. And it also uses the GNU Scientific Library to get stuff for you for the spherical phonics and some hidden routines. And there's some documentation that are provided by or produced by a tool called Forward, based on inline special comments that is available at that URL. Just a reminder before we go on to something else. Just a reminder of what the computational setup is. So we have a domain that goes from rho min to rho max. Rho min corresponds to the horizon. And in the region between rho min and T1, we use ingoing hyperboloidal coordinates, evolving the full singular or retarded field, and typically we use the coordinates tau and rho in that region. Then between T1 and W1, where W1 is the location of the world tube, we use time-dependent coordinates lambda and sigma, or lambda and psi, and in this region as well, we are evolving the full retarded field. Then between W1 and W2, the boundaries of the world tube, we are evolving only the regular field, and also doing that in the same time-dependent coordinates. And on the outside again, between W2 and T2, we are evolving the full retarded field in the time-dependent coordinates. And then between T2 and rho max or square plus, we are evolving the full retarded field in outgoing hyperboloidal coordinates. And so just to remind you that the rho min or H, T1, W1, W2, T2 are points, and as well as rho max are points that are fixed in the computational coordinate domain and stay at the same coordinates. And so we are placed at element boundaries so that we can take care of the discontinuities in the solutions and so on when we communicate the fluxes between the different domains. So before going on to the practical part of it, we do have other systems of equations in the pipeline. We have a Tucholsky solver in both Schwarzschild, written by IU student Sarah Skinner in 2019. This is essentially ready, but needs to be cleaned up and documented and checked. And also Kerr, I had a IU student last year, and this work was continued by another IU student this year, for essentially extending this to the Kerr case, where things get more complicated because you have to evolve modes that couple together. We have some development on the metric perturbations in Lorentz gauge, done by Samuel Kopp, my graduate student. And we also have a code where I wrote the original in the previous version of the code, and Samuel Kopp has been working on porting that to the new SelfForce1D infrastructure. Another student, Mary Ogborn, in 2020 started working on some checkpointing restart facilities, which is kind of useful when if you have to do long evolutions. But that needs more development before it can be used. What we also need is some high-level code documentation that explains how all the classes fit together. The documentation that I mentioned earlier essentially just documents the classes and so on, but we need an overall description of how everything fits together. And as I mentioned, the code is part of the Einstein toolkit and the black hole perturbation toolkit. And so my hope is that the code will be useful to a useful community resource that hopefully will inspire people to add stuff that can then be contributed back to both the black hole perturbation toolkit and the Einstein toolkit. And so the code is available on Bitbucket. This is the URL, and everybody can go in and check it out. So maybe before going to the practical parts, let me just pause here and ask if there are any questions.
I have a question.
Yeah.
So is this the particle point the only non-smooth point in the computational domain?
Yes. So the at the location of the particle, the effective source itself has limited smoothness exactly at the particle. But we also have the thing where we, in some regions, we evolve the regular field. In some regions, we evolve the full retarded field. And at those boundaries, in principle, the solution is discontinuous, but we can always add and subtract the singular piece to when we communicate the fluxes.
Okay. Then do we have a high order convergence at the particle point?
Yes, because when I keep the particle fixed at the particle location, the derivative operators or the derivative matrix calculations only see a smooth field. It never sees the discontinuity. So we maintain exponential convergence. So
the solution, the numerical solution is smooth everywhere, basically.
Yes.
Okay. Then why do we need this continuous Galerkin here? Because the solution is smooth everywhere.
Well, I mean, I mean, you could also do it with other methods, but the discontinuous Galerkin method is quite convenient and quite powerful and gives highly accurate results for a fairly low computational cost.
Okay. Thank you. I have another question. So what kind of flux do you use at the boundary?
I use a flux based on characteristic decomposition. So essentially, I decompose my fields into ingoing, outgoing modes, and then only provide. But the flux is constructed to only communicate the path that goes from one domain to the other.
Oh, thank you. Thank you.
Any other questions?
I don't think so. I don't see anything in the chat. So
okay. So
if no one speaks up, then we can continue.
Yeah. So let me go and let's see. So do I need to make this bigger, the font?
Maybe a little bit, if you can.
Okay. So you should all, if you go into the tutorial server, you should be able to launch this notebook here, SelfForce1D, like that.
Yeah. And just for everyone, as a reminder, Roland just posted the server URL and code again in the chat.
So maybe I'll make it one more. Somehow I have a window covering my scroll bar here. Okay, so the first thing is setting up all the magic that you have been seeing in the other tutorials as well, and nothing really goes on here except for that. So if you go and, well, just make sure that you're in your home directory. Then the first command here will essentially just, if you have already run this, it would just remove the SelfForce1D source tree and the examples that I provide. And so that goes up like that. And then we just have to execute a get clone to get the code from Bitbucket. And you can see it's already checked out. Doesn't take long. And after that, if you do an ls in your home directory, you should now see the SelfForce1D directory like that. And in order to go and do the compilation, we of course have to go into that directory. And as I mentioned, we use scons, which is a Python-based sort of make replacement where you can do all kinds of nice things in Python in addition to what you would normally do. And in this note, on this server, we already have a sconstruct file called sconstruct.fedora that will be able to compile the code. On other systems where GSL, BLAS, and LAPACK are not installed sort of in standard locations, of course we have to modify the sconstruct file to tell it where to find those libraries. But now let's just copy the sconstruct.fedora file into the name sconstruct. On this tutorial server, scons is already installed, but if it wasn't installed, you can do it very simply in your own user space by using pip like this. Here, when we do that, it says that the requirement is already satisfied because the package has been installed already. Just to get some nicer looking output from scons, we can also install something called term color git or term color. And again, this I thought it was already in there. Well, doesn't matter. So the tutorial server are an Ubuntu system, and as I mentioned, the Ubuntu G420 has some issues with my code, so we had to compile another version of GCC and G420 to support that. So in this cell, essentially we just export the path to that compiler and make sure that it does point to the right thing. Use a local GCC 8.4. For some reason, this export of that environment variable is not transferred from cell to cell. So every time we have to use the compiler, we have to do the export first. But now in order to build the code, we just again do the export of the path, and then we just call scons that will then look at the source files, figure out what order to compile them in. And so there's one file, the effector source, that takes a little while to compile, but it shouldn't be too bad, and then it will continue. Don't worry about the warnings here. This is just a warning from the compiler that a bunch of directories that I provide in order to where it should look for module files has not been created yet. But once the whole thing has been built once, those will be there and the warnings will go away. That's probably also a way of getting rid of the warnings by just changing the options. And you can see the compile continues. thinking, and S consists on building the targets. And so now inside the your SelfForce1D directory, there should now be a build directory where and then a build exe directory where the executables that have been built are placed. And these first two are just for testing purposes. The real executable is this one. I should probably at some point go and change the name to something more, something better than just test. Now let's try to run an example. So let's go back to the home directory and then create a directory for the examples that we're going to run. And change into the examples directory. The first example we're going to run is just does not actually use a point particle. It just uses sets up a Gaussian profiles for initial scalar fields, and so this will be kind of simple and fast. So let's make a directory for that and go into it. And of course, the code needs a parameter file, and Fortran has a convenient feature called name list, where that you can use to write very simple parameter files. So the parameter file has to start with an ampersand and then the name of the name list, and then it has to end with a slash. And then otherwise it's just the name of the parameter, an equal sign, and then a value. So if you look here, you can see we're using 32 elements. We're using 10th order elements. This is the lower coordinate of the horizon. We devise the other coordinates based on having the Gaussian centered around a radius of 10 in spatial coordinates. The mass of the black hole we set to 1. We only evolve from L equals 0 to L equals 2 modes. We evolve from 0 to 1000. The Gaussian has a width of 1 and amplitude of 1. And we activate some observers so we can extract the fields at the horizon, and that's y plus, and we specify how often to do the output. So fairly simple. So we write that into a file in that directory. And next, again, we have to export the library path, because now we actually do something where we need the Fortran libraries. We set the OMP numFest to 1, and then we can run it, the code by this command here. And you will see some output being generated. This test, if I was running alone on the machine, would take about 40 seconds, maybe a little bit more. So there's just wait until it finishes. I have another window here where, oops, I'll just go back. Okay, let me go here and my console or terminal. So I see my program has been running for 44 seconds and looks like it's finished, and I see some other codes are finishing. So, and it says that the program ended after almost 30,000 iterations or time steps. So let's just take a look at what happened here. So we ran modes 0 to 2, L equals 0 to 2, and let's just take a look at some of those files. So if you do an ls, you will find some files called that ends in .asc. Those are produced just ASCII files containing this one contains 1D data, and this one contains the fields extracted at the horizon and at Swipe Plus. So in order to look at the data, we have to read them in. So we import NumPy, and we just read in the extracted data for modes L equals 0, M equals 0, L equals 1, M equals 1, and L equals 2, M equals 2. And just printing out the first part, you can see that it's just a time series data with the time and then 4 columns of data, the real and numeric components of the horizon and that Swipe Plus. So we can just extract those into more conveniently named variables. And just to make plots look better, I figured out that you could get this tool here. And now we will do plots with matplotlib. I start by setting up some information about the size of the plots and so on. The standard matplotlib stuff. And now let's look at the L equals 0, M equals 0 mode in a log-log plot. And both at the horizon of future null infinity. If we just execute this, we should get a plot. And as you can see, we have the fields. So again, the blue is, oh, where does the legend go? Okay, maybe my, make it a little bit smaller maybe. Ah, here we go. They were pushed off the screen by my size here. So the blue is at the horizon, and Y is at, and the red is at Swipe Plus. And when we just set up a Gaussian profile, we would expect to see Gaussian mode ringing. With L equals 0, M equals 0, that phase is very short, and we'd only see a few cycles. So what we are focusing on here is the tail behavior. We expect that the field at late time should decay as a power law at both the horizon and Swipe Plus. At Swipe Plus, the power law should be the formula for the power law is -2L plus 3, and at Swipe Plus it's -L plus 2. And for L equals 0, we would then expect at the horizon to the field to decay as 1/t to the third, and at Swipe Plus at 1/t to the second, and this is exactly what we see here. If we plot in a log plot the data for L equals 1, M equals 1, we are now in a where we can see more of the quasi-normal mode ring down phase. And what I overplotted here with the black is the expected frequencies based on some calculations from Emanuel Berti. And so you see we do get quite nice overlap for a long period of time, showing that the code is producing the right frequencies. And at the end, when here, of course, we have the transition from quasi-normal mode ring down to the tail, and so we will start to see deviations there. If we look in a log block plot for L equals 1, M equals 1, again, you can see that the field decays
5 minutes
as expected 1 over t to the 5 near the horizon, and 1 over t to the 3rd at 5 plus. I will skip the plots of the L equals 2. They're simply the same as L equals 1. Let's go and take a quick look at an example with a particle source. So let's go back up one. Now we make another directory for this case with an effective source. I call it scalar elliptic 6 because I will use 6 order elements, and it's on eccentric orbits. And go into it. And here I will extract some initial data files from a directory on Steve Brand's account, just to have good initial data for L equals 0 to 2. And you can see the parameter file is a bit more complicated. Here we're using 28 elements of order 6. We have moved the inner boundary coordinate location a little bit. We're using a eccentric orbit with 9 point simulator spectrum 9.9, eccentricity 0.5. We are using a particle. We are evolving L equals min to L equals 5. Let's see, what else do we have? We are using the world tube. We're using a generic orbit, and we're using the oscillating orbit framework for evolving the orbits. And we specify where the initial data are located, and set up the correct initial phase for the particle orbit to be consistent with the initial data. We set the charge of the particle to be 1/8. It doesn't really matter what we set it to unless we actually start applying the back reaction. Now, you shouldn't run this right now. You can run it later when the machine is not so busy. This is a run that will take about 40 minutes to run. So, yeah.
Before you continue, quick question in the chat. How do you generate the initial data? Do you use the Einstein toolkit for this?
No, for the initial data, that's with the SelfForce1D, there's a Python code written by Nils that we can use for generating the initial data.
2 minutes.
So it's part of the toolkit of the code here.
Okay, thank you.
So I saved, ran this earlier, and I should. So I will copy those files to the directory here instead of running it right now. Like that. And now I should be able to plot some things. I should have the data here. And I will extract the radial component of the SelfForce data and read them into NumPy, and then plot them with
1 minute. Please conclude.
With matplotlib. And what you see here is essentially a bunch of, so I only used initial data for L equals 0, 1, and 2. So you can see they start up with smooth initial data. Then I had to turn on the source for the remaining ones. And so you see all these transients. And then they settle down. And eventually at the end, you can see
30 seconds. Please conclude.
Extracted right in the right way, and that the amplitude of the higher modes decrease as we would expect. And the final thing is just plotting the radius that we actually evolved on, and you can see that this is indeed an eccentric orbit. And I will stop here.
Brilliant. Thank you so much, Peter. That was amazing. Do we have any more questions from the audience? Okay, doesn't look like it. So I would say we stop here. This is really impressive. So thanks again, Peter. Oh, wait, stop.
So just one thing. I have to leave and won't be here for the tutorial help in the afternoon, but I will be around for the tutorial help in the morning tomorrow morning, and as well tomorrow if anybody needs help with some of this stuff.
Yeah. Okay, brilliant. So we have one more question in the chat. Sorry. So the question is, what are those sharp peaks for L = 1 in red?
Okay. This is essentially, because we plotted this is in a log plot. This is just where the self force crosses 0. So we have positive values on one side and negative values on the other side. So it's not actually a sharp feature in the actual extracted mode.